Welcome to the MOOC of Econometrics. So far, we have learned several topics under this heading, Econometrics. Out of these several topics, one of the major topics is probability theory and another key topic is inference. Today, we will consider summing up of these two topics which we have learned so far. So, today we will not go into any particular segment of these two topics, but we will try to give you an overall idea of the whole thing. So, let us start with random variables. What is a random variable? Given a sample space, you know what is a sample space already. Given a sample space omega, a random variable is defined as a real valued function defined on this sample space. So what do we mean by these two criteria? That it's a real valued function defined on the sample space. Firstly, a random variable has to be defined on the sample space means whenever we conduct a random experiment, there will be several outcomes and the collection of all such outcomes is a sample space. So random variable is basically a function on this sample space, and what kind of value does this function give us? Real valued functions. If we go to an example, we toss a coin 3 times. So what are the possibilities? One may get 3 heads out of these 3 tosses, that is H may be the outcome, or one may get 2 heads and 1 tail. So there are 3 possible outcomes with respect to this, HHT, HTH, THH. Similarly, one can get 1 head or no head. See, in all, we have already seen earlier also that there are 8 such possible outcomes. Now, we are defining x to be a variable as the number of heads obtained in these 3 tosses. So, when the outcome is HHH, evidently the value of x will be 3. When the outcomes are HHT, HTH or THH, obviously x will take up the value 2. Similarly, x will take up the value 1 for other 3 outcomes, and when the outcome is TTT, then x will take up the value 0. So you can see that for each possible outcome in the sample space, x is taking up a real number. So that is why x is a real valued function, a random variable is a real valued function defined on the sample space. In particular, in this example, x takes up the values 0, 1, 2 and 3. Random variables may be of 2 types, discrete and continuous. What is a discrete random variable? A random variable that can assume some isolated values is called a discrete random variable. We can take an example. We toss an unbiased coin twice. The outcomes are HH, HT, TH, TT. Once again, we define x as the number of heads obtained in 2 tosses. So you can see very easily that here x will take up the values 0, 1 and 2. You can see on the slide. What are the corresponding probabilities? Since the coin is unbiased, the probability of getting HH will be 1 by 4. There are 4 possible outcomes. One of those is HH, so 1 by 4. So similarly, probability that x will take up the value 1 is half 1 by 4 plus 1 by 4. And then x takes up the value 0, that is the outcome, probability that the outcome is TT is again 1 by 4. So that the probabilities will add up to 1. So on your slide you can see the probability distribution of this random variable. Now here the random variable takes isolated values, 0, then 1, then 2 and so on. That is why it is an example of a discrete random variable. On the other hand, a continuous random variable is that which can assume an uncountably infinite number of values within its range of variation. Obviously, from the definition, it will not be very clear to understand, but if we take an example, then it will be clearer. For example, you measure the weight of a randomly selected person. So, x is the weight of a randomly selected person. What are the possible values that x can assume? Any value between say 40 kgs and say 100 kgs, any value. So x can take up an uncountably infinite number of values within its range of variation, and in this sense x is a continuous random variable. Now we come to a very important concept, cumulative distribution function or distribution function, simply. So the CDF, which is abbreviated, of a random variable we define as fx, that is probability capital X less than or equal to small x, where small x is any value of capital X and small x is a real number. So that is why we have written for all x belonging to the real line. So in particular, suppose x takes up the value 1, 2 and 3. So what will be f2? Probability x less than or equal to 2. As you can see on your slide, the definition is clear. Probability density function. Now see, when x is a discrete random variable, we can represent the distribution of x by a table. The table will show us what? The values of this random variable together with their corresponding probabilities, and it has to be noted carefully that the total probability will be 1, because we have seen earlier also that the total probability in a sample space is 1. Random variable is a function defined on this sample space, so the total probability corresponding to the different values of a random variable should also be equal to 1. So this is how we represent a discrete random variable. We have seen in the last example. But how to represent a continuous random variable? The probability distribution of a continuous random variable cannot be represented in terms of a table. Why? Because a continuous random variable assumes an uncountably infinite number of values, not isolated values or discontinuous values. So we have to represent the probability distribution of a continuous random variables in terms of a function known as probability density function, which is abbreviated as PDF. So you can look at the definition on the slide. A random variable x is said to be absolutely continuous, or alternatively is said to have an absolutely continuous probability distribution if and only if there are two conditions: non-negative, first condition, and integrable. So if and only if there exists a non-negative integrable function f, small f, such that the CDF f, we have already defined CDF, the CDF f may be written as fx equals to integration from minus infinity to x ft dt, where x belongs to the set of real numbers. So this small f is the PDF, and this PDF has definitely a relation with CDF, because by integrating the PDF we get the corresponding CDF. So this is to be remembered. We have studied several distributions, several theoretical distributions under the topic random variable and its probability distribution, and the most important one of those is normal distribution, because we have already seen there are several applications of normal distribution. Actually, in almost all walk of life, whenever we consider continuous random variables, we can use normal distribution. So it is better to recapitulate the normal distribution once again in a different light. A continuous random variable x is said to follow a normal distribution if its PDF is given in this fashion. As you can see on your slide, it's 1 by sigma root 2 pi e to the power minus half x minus mu by sigma whole square, and x can take any value between minus infinity and infinity. Now you can see there are two constants involved in this function. One is mu and the other one is sigma. So mu, which is the mean of the normal distribution, can take any value between minus infinity and infinity, while sigma will take up only positive values between 0 and infinity. So here mu and sigma are the two parameters of the distribution, and we use the notation x follows normal mu sigma or x follows normal mu sigma square. There are several properties of this distribution. Two most important ones are the mean and the variance. That is, the expectation of x, where x follows a normal distribution, is mu and its variance is sigma square. And a normal curve is a bell-shaped symmetric curve, as you can see on your slide. It's bell-shaped, you can see from this, and symmetric in the sense that you can see both the tails of the distribution are more or less similar. That is, they are more or less equally spread towards the positive as well as the negative direction of the x-axis. So this is a normal curve. We need to know how normal distribution looks like, because normal curve comes in handy in many situations, many practical situations. So that is why this is important. We consider some applications of normal distribution. Suppose x follows a normal distribution with mean say 12 and standard deviation 4. We have to find out probability x greater than 20, and we are given the CDF of a standard normal distribution for the value 2, which we denote by capital phi 2. The value is given, and this value can be obtained from any statistical software, even the very simple statistical softwares, and also it is tabulated in Biometrical Tables Volume 1 by Carl Pearson. So these values will be given to us, the values of the CDF. So here mu is 12, sigma is 4, standard deviation is 4. So probability x greater than 20, we can always write 1 minus probability x less than or equal to 20. Now we can also write probability x less than or equal to 20 as probability x minus mu by sigma less than or equal to 20 minus mu by sigma. You're subtracting mu from both sides and dividing by a positive constant. So the equality or inequality remains the same. So x minus mu by sigma is what? A standard normal variate, which we can denote by z. Normally it is denoted by z. So we write 1 minus probability z less than 2. Deliberately I have written less than 2, not less than or equal to 2, because for a continuous random variable, less than and less than or equal to mean the same thing. Similarly, greater than and greater than equal to will also imply the same thing. So that is why deliberately in one step I have written less than equal to, and in the next step I have written less than, so that we can come to understand that both are same things. So probability z less than 2 is again capital phi of 2. So we have the probability as 1 minus capital phi of 2. The value of capital phi of 2 is given, so we can get the corresponding probability. So this is one application of normal distribution. So similarly we can have several such applications of normal distribution. We shall now consider the next section of our talk, which is the elements of sampling distribution. If you can recall, we have said that it is not always possible or feasible to enumerate the whole population. So we have to resort to sampling. Let me explain this by an example. Suppose my objective is to find the per capita income of the adult Indians. What do you mean by per capita income? Total income divided by the number of individuals, which is per capita income. Now you can imagine, if I want to find out the per capita income of adult Indians at a specific time point, what data I have to collect? I have to collect data on the income of each and every adult Indian, which is a huge task. We cannot perform this task every now and then. So what else we can do? We can select a part from this whole Indian population, which we call sample, and on the basis of this sample data, we can infer or guess about the corresponding population characteristic, that is the per capita income of the whole Indian population. Now we have to understand one thing, that suppose I draw a sample and in my sample I deliberately take all the rich persons. Then if I use this sample characteristic as a representative value, as a reflection of the population characteristic, shall I be doing justice? Obviously not. Similarly, if my sample contains only the poor persons, will that justify my investigation? No. So we have to take the sample in such a manner that the population of different segments or all possible segments are represented in my sample. That means I have to select the sample following certain procedures. So that is why we have to learn sampling distribution and the key topics under this sampling distribution. So let us go into this. By definition, a population is the totality of individuals or objects belonging to a given field of inquiry. For example, collection of all students of a college, collection of all commodities in a market. So these are all populations. Suppose I want to know about the curriculum structure of a given study program. So what will be my population? My population will be all the students who are studying that curriculum or who are studying in that college. So that will be my population. Similarly, suppose I want to get an idea about the average price level of different commodities available in the market. So what data I have to collect? I have to collect data on each possible commodity from the market. So that means collection of all commodities in the market will be my population in that case. So it is a collection of individuals or objects belonging to a given field of inquiry. The totality of this thing is called a population. A sample, as I've already mentioned, is a part of the population which is meant to represent the whole population. So we can say a group of students consisting of 5 students from each stream may be my sample in the first example, because I might not be able to collect data from each and every student belonging to that college. So I select some students from that college in my sample. Similarly, it might not be possible for calculating the price level to collect data for each and every commodity that are available. Because why this is not possible, you see, one simple example, say rice. What do you mean by price of rice? It doesn't basically carry any meaning because there are different brands and qualities of rice. So that means even for rice, if I want to collect data on price, I have to collect so many data points. We have to collect so many data points. So that is why it might not always be possible to collect data from this totality. So we can select a list of commodities used by an average family. Average family means normal family. So that is my sample in this situation. Important thing is this, as I mentioned, that we have to know how we can select a sample from the population so that the sample becomes a true representative of the given population. One of the criteria is you take the sample randomly. That is, you consider a random sample. We'll try to explain this with the help of an example. Suppose there are 6 members in a population and a sample of size 2 is to be selected. For this, suppose we throw an unbiased die twice. In the first row, if 5 comes, then the 5th member I can select in my sample. I throw it again. If I get, say, 2, then the second member will be included in my sample. So you see, it can easily be observed that here each member is getting the probability 1 by 6 of being selected. That means there is a chance, or to be specific in this particular example, there is equal chance of selecting each member into my sample. So this is random sampling. That is, each member has got a pre-assigned fixed probability of being included in my sample. I am not deliberately choosing one individual. I am not giving preference to one individual or object over another. There are basically 2 types of random sampling. One is simple random sampling with replacement, and the other one is simple random sampling without replacement. When we call it SRSWR, that is simple random sampling with replacement, if each member or unit of the population are selected one by one in the sample, and after each selection or drawing, the member selected is returned to the population in such a way that at every selection or at every drawing, each of the population members gets the same probability of being selected. The formal definition you can see on your screen. So what does it basically mean? There is a population from which we'll select sample. I select one individual or object. I note down the variable of interest. Suppose I am interested in income. So I note down the income of the individual and return him to the population. So that means the same individual in this sampling scheme, the same individual can be selected once again in my sample. That is simple random sampling with replacement. On the other hand, there is another type of sampling which we call SRSWOR, which stands as an abbreviation of simple random sampling without replacement. So the sampling is said to be without replacement, or SRSWOR, if each member or unit of the population are selected one by one in the sample, and after each drawing the member selected is not returned to the population. But they are not returned to the population in such a way that at each drawing, each of the remaining members will get the same probability of being selected. So here also again we will choose one individual, we will note down his, say, income, but we will not return him to the population. That means that particular individual or that particular member will not be selected once again in my sample. So the basic difference between SRSWR and SRSWOR is this, that in SRSWR, the same population member may be selected more than once in a sample, but in SRSWOR, the same population member cannot be selected more than once in the sample. But in any case, at any drawing, the probability of selection remains same for all the individuals. That means both SRSWR and SRSWOR ensure that there is no preference of individuals or objects for selecting in the sample. So in this sense, these are random samples. Now we come to the next definition, which is sampling distribution. You can understand, I want to know the population per capita income. So it's some sort of an average. So I'm interested in population average. But I'm not being able to enumerate the whole population, so I have to resort to a sample. So what I can do, I can calculate the sample mean. Now you will be appreciating this fact that population mean in any particular situation is a constant. It cannot vary. For a given population, it's constant. But what about sample mean? Suppose I select a sample and you select another sample. So my sample may be different from your sample. So my sample mean may be different from your sample mean. That means a sample mean can vary from one sample to another. And we have already seen earlier when we discussed these things in details that a population characteristic is termed as a parameter while a sample characteristic is termed as a statistic. That means a parameter in any given field of inquiry, in any given investigation, is a constant while a statistic may vary. So this variation in the values of a statistic is called its sampling fluctuation. Now see, a statistic is nothing but a random variable because it is generated from a random sample, so it will be a random variable. So a statistic is a random variable and it varies. So that means a statistic will have a probability distribution. Today, right, just a few minutes back, we have studied probability distribution. This probability distribution of a statistic is called sampling distribution, right? So the formal definition is on your screen. You can see that. There are basically three important sampling distributions: chi-square distribution, t distribution, and f distribution. So we start with chi-square distribution. A random variable has a chi-square distribution if it can be written as the sum of squares of independent standard normal variates. We know standard normal variates, the variates have to be independent. The sum of squares of such variates will be a chi-square variate, or will follow a chi-square distributions. Sums of this kind are encountered very often in statistics, especially in the estimation of variance and in testing of hypothesis. You can see the curve of a chi-square distribution on the screen. You can see it's a positively skewed curve and it varies from 0 to infinity. Next we move to t distribution. Suppose z is a standard normal variate and chi-square is a chi-square variate with n degrees of freedom. Now what do we mean by n degrees of freedom? Recall, what is chi-square? Sum of the squares of some standard normal variates. If we take 5 standard normal variates, then the chi-square distribution will be of 5 degrees of freedom. If I take 10 standard normal variates, then it will be of 10 degrees of freedom. So in general, if I take n number of standard normal variates independent and consider their sum of squares, then it will be a chi-square variate with n degrees of freedom. Further, suppose z and chi-square are independently distributed. We define, as you can see on your slide, a t distribution as a t statistic as z by square root of chi-square by n. T is then said to follow a t distribution with n degrees of freedom. You can see the curve of a t distribution which is symmetric in nature and the point of symmetry is 0. Next one, f distribution. We consider two independent chi-square variates, chi1 square and chi2 square. The first one is having n1 degrees of freedom while the second is having n2 degrees of freedom. And chi1 square and chi2 square are independently distributed. We define f as chi1 square by n1 divided by chi2 square by n2. That is basically chi square by its corresponding degrees of freedom, both in the numerator and in the denominator. F is said to follow an f distribution with, now there are 2 degrees of freedom. Unlike chi square and t, there are 2 degrees of freedom, n1, n2. The first degree of freedom is the degree of freedom of the numerator, while the second one is that of the denominator. So that is f distribution. And you can see the f distribution's curve on your slide, and it is quite clear or quite evident that it is a positively skewed curve. Again, it varies from 0 to infinity. Immediately after sampling distribution, what we study is statistical inference, which is the key topic of statistics. Actually, we study statistics because we want to infer the unknown nature of the population from the known nature of the sample. Any statistical inquiry has as its goal the acquisition of knowledge about some unknown characteristics of a population, which we call a parameter. It may be population mean, it may be population variance, it may be some other characteristic of the population. The inquirer will generally have information regarding a random sample drawn from this population. That means the inquirer will not have information regarding the whole population, but the inquirer will have information regarding a part of it, to be specific, a representative part of it. The central problem of statistics is then to work out methods of inferring the nature of this unknown parameter from the known nature of the sample. This is the basic problem. This is the central problem of statistical inference. There are two broad types of statistical inference. The first type is estimation. What is that? The characteristics of the population, what we are interested in, may be completely unknown, and we may have to depend entirely on the sample observations to form an idea about these characteristics. Now, the population characteristics is completely unknown. For example, I want to find the per capita income of adult Indians, which is unknown to me. Because we know Indian census is carried out only once in 10 years. So after the census, even in the following year of census, there is no data with me for the whole population. So that means that this parameter is completely unknown. I have a sample. Obviously, I can draw a sample. I want to know the value of this unknown parameter. I want to know the value of this unknown parameter. So this problem is called estimation. How do I know this value? Obviously on the basis of a sample. This estimation may again be point estimation or interval estimation. In the first case, that is in case of point estimation, the name justifies it, point. We take a point. That means we take a single value on the basis of the sample observations and put forward this value as a likely value, which we call in technical term an estimate of the unknown parameter. The statistic which is used for this purpose is called an estimator, and its value for a given set of sample observations is called an estimate. Again, I come to my favorite example of this per capita income. I want to know the per capita income. So I cannot enumerate the whole population, so I take a sample. From that sample, I calculate the sample mean. Because in many situations, it can be seen that sample mean is a good approximation or a good guessing value of the corresponding population mean. That means I decide that I will estimate the population mean by sample mean. Fine. This sample mean will be called an estimator for the population mean. Suppose I find the value of this sample mean is 12,000. Then this 12,000, this value 12,000 will be called an estimate. So the statistic which is used for estimation is called an estimator, and its value for a given sample is called an estimate. Now why I am repeatedly saying for a given sample? You see, I take a sample, I get the sample means 12,000. You take a sample, you get the sample mean 13,000. That means the estimate can vary. It will depend on the sample that I have chosen. So that is why we stress upon this fact that the sample should be appropriately chosen so that it can truly represent your population. So this is point estimation because we are just computing one value. On the other hand, one may think that they will say that the population mean will be somewhere between 10,000 and 15,000. 10,000 and 15,000. So that means instead of a single value, one may estimate the parameter in terms of an interval. This will be called interval estimation. So you can see the formal definition. In the latter case, that means in case of interval estimation, we compute two values on the basis of sample observations and put forward the interval between these two values as likely to contain the true value of the parameter. So the first kind of statistical inference is consisting of this estimation, point and interval. What is the second type of statistical inference? In the second type of statistical inference, we start with some tentative idea regarding the unknown parameter. And we use the sample observations to judge how tenable this idea is. What do you mean by all these things? Suppose I am the manufacturer of, say, electric bulbs, and I say that 0.1% of my products are defective. How do I know? Have I investigated each and every bulb produced by me? So it's not a concrete idea, it's a tentative idea that 1% or 0.1% of my products are defective. Now, as a customer, suppose you buy the bulbs from me. So as a customer, will you accept what I say? Obviously, you'll see. So you'll buy some bulbs from my manufacturing unit. So this some bulbs is a sample. So on the basis of this sample, you'll judge how tenable, how justifiable my idea is. This tentative idea will be called a hypothesis, and the process of judging its validity is known as testing of hypothesis. This is the second kind of statistical inference. We have talked about estimation. So estimation obviously will lead to an estimator. So there might be several estimators for a given parameter. So we have to choose judiciously which estimator we will be using. So we consider criteria of a good estimator. So one can think of several estimators of a parameter, population parameter. For example, one may try to estimate the population mean, maybe by sample mean, or may as well by sample median. Hence, it is essential to fix some benchmarks for an eligible or a good estimator. The first criteria is unbiasedness. A statistic T is said to be an unbiased estimator of a parameter theta if expectation of T is equal to theta, whatever be the true value of theta. So why this criteria is required? Expectation of T is theta. We have seen earlier that expectation is nothing but the arithmetic mean in the probability setup. So this criteria, expectation of T is equal to theta, ensures that different values of T for different samples will be clustered around theta. So whichever sample I observe, I will observe only one sample. So whatever sample I observe, if I calculate the value of T from that sample, this criteria will ensure that that value of T will be close to theta. So that means I will not be prone to a large magnitude of error. So this is the first criteria of a good estimator. We take an example. Suppose P is the probability of getting head in a single toss of a coin. Suppose my objective is to estimate P. For this purpose, we toss the coin a number of times, say n times, and suppose X be the number of heads obtained in these n tosses. We know that X will follow a binomial distribution with parameters n and P. So expectation of X will be NP, n into P. So that will basically mean, with a little algebra, that expectation of X by n will be equal to P. So that means according to the definition of unbiasedness, X by n, that is a sample proportion of getting heads, will be an unbiased estimator of P. We complicate the things a bit. We take the second example. Suppose x1, x2, xn is a random sample drawn from a population with some mean mu and some variance sigma square. Then obviously expectation of xi will be equal to mu for all I running from 1 to n. Also, you can see on your slide, if I work out expectation of x bar, that will also come to be equal to mu. Now, if my objective is to estimate mu, then how many unbiased estimators do I get? You see the first line, expectation of xi is equal to mu for I equals to 1 to n. That means n estimators are there which are all unbiased because expectations are mu. Also x bar, expectation of x bar is also equal to mu. That means we have here n plus 1 unbiased estimators of mu. So as far as the first criteria is concerned, all these n plus 1 estimators are equally good. So which one will you prefer? So that means only the first criteria will not tell us how to choose a good estimator. So we have to go to the next criteria, which is called minimum variance. A statistic T is said to be a minimum variance unbiased estimator, abbreviated as MVUE, of a parameter theta if it is unbiased, that is expectation of T is equal to theta, and variance of T is less than or equal to variance of T dash, where T dash is any other unbiased estimator of theta. So that means, what is a minimum variance unbiased estimator? You have several unbiased estimators. First of all, that estimator has to be unbiased, and if you have several such unbiased estimators, you choose that one which has got the minimum variance. So in any practical situation, when you'll be faced with a number of estimators, how will you choose the best among them? First, you choose those out of the given estimators which are unbiased. Suppose 10 such estimators are available, you choose those which are unbiased. Suppose several of these 10 estimators are unbiased. You first filter out those. In the next step, out of these 7 unbiased estimators, you choose that one which has got the minimum variance. That will be your best estimator. So in the present case, what we have, variance of xi is sigma square for all I because it's a random sample. Also, we can work out variance of x bar, it will come out as sigma square by n. So we had n plus 1 unbiased estimators. What are those? x1, x2, xn and x bar. x1, x2, xn has got the variance sigma square, x bar has got the variance sigma square by n. So which is the minimum variance among these n plus 1 unbiased estimators? Evidently x bar. So thus x bar has the minimum variance among the n plus 1 unbiased estimators of mu. Hence, x bar is the best among these n plus 1 unbiased estimators. We now come to the second type of statistical inference, which is called testing of hypothesis. Here we start with some tentative idea regarding the unknown population. And obviously, as I have said, on the basis of the sample observations, we are going to judge how tenable this idea is. This tentative idea we call a hypothesis, and the process of judging its validity is termed as the testing of hypothesis. By tentative assertion, we really mean the assertion that has to be verified on the basis of the sample observations. That means in the light of the sample observations. This verification of any statistical hypothesis on the basis of sample observations is known as testing of hypothesis or test of hypothesis. When we consider testing of hypothesis, there are two types of hypothesis: null hypothesis and alternative hypothesis. Null hypothesis is that which is tested, and alternative is that which contradicts the null hypothesis. We take an example. Suppose P is the probability of getting head in a single toss of a coin. I want to test whether the coin is unbiased. That is, what is my null hypothesis? P is equal to half. So what can be my alternative hypothesis? The coin is not unbiased. That is, P is not equal to half. So H naught here is the null hypothesis and H1 is the alternative one. We have said that any hypothesis, or to be specific, the null hypothesis, will be tested on the basis of the sample observations. That means we need a sample characteristic which will tell us, the value of which will tell us whether the null hypothesis is to be accepted or rejected. The sample characteristic that tells us about this, or that guides us towards the acceptance or rejection of the null hypothesis, is called the test statistic. Suppose in the previous testing problem, for P equals to half against P not equal to half, we toss the coin 10 times and X is the number of heads obtained. So X by 10 is the sample proportion of heads. So X by 10 may be considered as a test statistic in this situation. Normally we denote a test statistic by capital T. Critical region, very important. Now see, the values of the test statistic, or the value to be specific of the test statistic, will dictate me, will tell me whether to accept a null hypothesis or reject a null hypothesis. A test statistic may have several values because it's a random variable. So for some values we will accept the null hypothesis, and for some values we will reject the null hypothesis. The set of values of the test statistic that will lead to the rejection of the null hypothesis is called the critical region of the test. We normally denote it by W. The set of all possible values of the test statistic is denoted by script X. You can see a symbol on your slide which is script X. The script X may be divided into two mutually exclusive subsets, W and W complement. If T, the test statistic, belongs to W, we reject the null hypothesis. On the other hand, if it belongs to W complement, then we accept this. This W and W complement are respectively known as the critical region and the acceptance region of the test. In this problem, we toss the coin 10 times, and suppose we decide to reject H naught, that is, reject the hypothesis of unbiasedness, if we get too little number of heads or too much number of heads. Say if I get less than 2 or more than 7 number of heads, we reject the null hypothesis. That means here the critical region will be what? 0, 1 on one side, which is less than 2, and more than 7, 8, 9 and 10. And obviously you can see script X, which we call the sample space, is a set of all possible values of the test statistic. When we toss a coin 10 times, what are the possible number of heads? We may not get any head at all. We may get 1 head, 2 head, and we may get, in all the tosses we may get heads. So X can take up the values, or the test statistic can take up the values 0, 1 to up to 10. So that set will be our sample space script X. So here critical region we have seen. So what will be the acceptance region? It's complement. That means it will take up it will constitute the values 2, 3, 4, 5, 6 and 7. So this is in a nutshell the whole thing. We have true states, H naught is true, H naught is false, and we can take two types of decisions. Either we can accept H naught or reject H naught. So if H naught is true and we accept it, obviously we take a correct decision. If H naught is true and we reject it, we commit one kind of error which is called type 1 error. If H naught is false and we accept it, that means again we are committing some error which is called type 2 error. And when H naught is false and we are rejecting it, again we are taking a correct decision. There are 4 types of things that can emerge in any testing problem, which we call an error table. This is important, level of significance. You see, obviously we'll try to minimize in our procedure both the types of error. But we cannot minimize both the types of errors simultaneously. If we try to reduce type 1 error, then that will result in the maximization of the type 2 error. So we fix an upper bound to the probability of type 1 error, and then under this restriction try to minimize the probability of type 2 error as far as possible. This upper bound to the probability of type 1 error is known as the level of significance of a test. Normally we use the level as 0.05 or 0.01, which we term as 5% test or 1% test. So these are the important topics that we have covered so far in a nutshell today. Obviously when you'll be applying these topics, you have to study the topics in details as we have done earlier. In our earlier study materials, you can go back. But to get an overall idea about the whole thing, you might require this particular lesson plan. Thank you.